Thank you very much. I'm going to talk to you in the next few minutes about groundwater baseline sampling programs designed to identify potential leakage from unconventional gas plays in Alberta, Calgary. And I want to first thank my co-authors, Pauline Humez, who is in the audience, Jennifer Ng, and Michael Nightingale, who have contributed significantly to this work. Now, in Canada, development of unconventional gas resources, just the way it's everywhere else, often is affected by public controversy between the rapidly expanding oil and gas industry and unconventional resources, facilitated by horizontal drilling and hydraulic fracturing, and the fear of landowners that some of their groundwater may be negatively impacted. The negative impacts on the groundwater can in principle come from three different areas. One is stray gas contamination, where methane is the major compound. The second would be formation waters, which are often high TDS. And the third is fracking chemicals used in the hydraulic fracturing operations. Now, it turns out at least 2 years ago, there was an astounding lack of high-quality scientific data in the peer-reviewed literature reporting on groundwater quality in the vicinity of oil and gas wells, and closing the science gap, we believe, is highly beneficial for a responsible development of these unconventional energy resources. So the objective of my talk today is to present to you the progress made in Alberta on baseline groundwater monitoring approaches capable of generating scientifically defendable data, based on which it can be assessed whether there is impact or there is a lack of impact from the development of unconventional gas resources on the quality of shallow groundwater. And my emphasis today is on shale gas and stray gas leakage. Now, this is a diagram which you probably have seen before, and the previous talks have mainly focused on the Marcellus Shale over here. I want to focus your attention to the top left part of this diagram. Shows you the provinces of British Columbia, Alberta, and Saskatchewan, and here we have various unconventional gas plays. There's the Horseshoe Canyon Formation, which is a major CBM play, which is mainly located in the southeastern part of the province of Alberta. And if you go to the northwestern part of Alberta and the northeastern part of British Columbia, we have the Duvernay, the Montney, and the Horn River, which are all three major shale gas plays. Now, the key ingredients to monitor for stray gas contamination is really threefold. It's widespread sampling and analysis of either dissolved or free gases from groundwater samples to establish a good baseline condition. Second, to collect information of chemical and isotopic compositions from the intermediate zone where leakage often occurs from, and that can be done during drilling operations. And thirdly, collect information of chemical and isotopic compositions of gases from the production zone itself. So the specific objectives of my talk today are to figure out how variable are key baseline parameters in groundwater sampling, which parameters are most diagnostic to detect stray gas contamination, and finally, is there a difference between using dedicated monitoring wells versus using landowner wells to assess baseline conditions in shallow aquifers. Now, in Alberta, the regulations state that free gas sampling is the major approach which should be used for groundwater baseline sampling. Here's a diagram showing you temperature versus the amount of methane you can potentially dissolve in a water sample. So the Alberta regulations ask for free gas sampling. They have designed special free gas sampler where groundwater is pumped in. The head space starts to fill up with the gases. These gases can then be transferred into Tedlar bags and returned to the laboratory for chemical and isotopic analysis. In our research group, we analyze these samples, but we also take dissolved gas samples, use the inverted bottle technique, which was cited before, and then take the samples back for chemical analysis using GCs, and for isotopic analysis, fingerprinting the carbon and the hydrogen isotopes of methane and higher alkanes wherever they exist. So the first program I want to introduce is the so-called GOWN network. It's the Groundwater Observation Well Network, which has more than 200 different monitoring wells, dedicated groundwater monitoring wells throughout the province of Alberta. Since 2006, 50 of these wells have been annually sampled by experienced staff from the government. Water and dissolved gas and free gas samples were obtained and submitted to laboratories. Most of these wells are completed in single formations, and finally the samples are submitted to only 2 specialized labs which do chemical and isotopic analysis. From this GOWN database, this is a diagram showing you the province of Alberta, and all the orange dots you see, this is where free gas has been obtained in shallow groundwater. There's a wide variety of various samples over here, mainly in the southeastern part of the province where the CBM play is relatively shallow underneath. Many of these wells have been sampled at least twice since 2006. And there's a purple dot over here, which is Mystic Lake well, which has been sampled more than 15 times since 2006. And for that well, I want to show you some of the data we have obtained. This diagram shows you methane concentration in free gas from this one well, which has been revisited 15 times. And the methane concentrations are quite variable, as you can see, initially higher than 30%. Then dipping down to less than 15%. The average value is 19.7% of methane in the free gas sample, but with a significant variability, and believe that is in part due to operational issues to setting up, because these are triplicate samples taken on the same day. And you see even on the same day there is significant variability in the methane concentration obtained. There's, however, also the opportunity that there are natural variabilities in these methane concentrations. We believe that on the left-hand side you see the same free gas methane concentration data set you have seen before. This is the same samples taken for dissolved gases, much lower concentrations obviously, but in generally we see the same trend, elevated methane concentrations initially, then a decreasing trend and coming back up. And again, these are duplicate samples from the same day, and they show, again, significant variability, believed to be both natural and operational in the causes. Now, if we move on and analyze the carbon isotopic fingerprint of these samples, then you see that the carbon isotope values are essentially constant. The average value is minus 78.5 per mil. The variability over 8 years is less than 2 per mil. And that clearly suggests that the methane here is from the same source, despite all the concentrations variabilities you have seen. The carbon isotope fingerprint is always the same. Of course, we can use the carbon and hydrogen isotope fingerprint to assess where the methane comes from. Biogenic gas, and this is a landmark paper by Mike Whittaker published in 1999. Carbon isotope values of biogenic gas typically between minus 55 and minus 110 per mil. Hydrogen isotope values of methane also very negative, typically for biogenic methane. In contrast to that, if you had thermogenic methane, carbon isotope values are typically higher than minus 60 per mil. Put the barrier here to minus 65 per mil to include very immature, shallow thermogenic gas. And also the hydrogen isotope values are typically higher if you have thermogenic methane. So if we apply this fingerprinting tool to the data from the GOWN network, you have methane concentrations here on the y-axis, carbon isotope values of the methane on the x-axis. We see a high variability of methane concentrations. This is now for 43 different GOWN wells in the province of Alberta. High variability in methane concentrations. Carbon isotope values invariably range from minus 58 per mil all the way down to minus 94 per mil. If we take the average value, we come up somewhere around minus 69 per mil, indicating that this is a mainly biogenic gas. If we then add to the carbon isotope values of the methane, which you have just seen for the 43 free gas samples from the 43 different GOWN wells, the hydrogen isotope values, they range typically between minus 260 to minus 320 per mil, on average minus 290 per mil. And again, that is an indication that the shallow methane in the groundwater is predominantly of biogenic origin. So this is now a summary plot showing you the carbon and hydrogen isotope values for the groundwater methane samples we have obtained in Alberta. We also show groundwater samples from the Appalachian Basin, which were previously published, both of these indicating biogenic sources of the methane for almost all the samples we have analyzed. And on the right-hand side, you see examples of isotopic fingerprints, both from unconventional and conventional gas plays, which are thermogenic in origin, and you can clearly see that they would be isotopically distinct. So if we now move on and look at what the produced gases look like isotopically and how different they are, we have to have a quick look at the hydrostratigraphy of the Western Canadian Sedimentary Basin. Here in the Quaternary and Tertiary, this is where most of our shallow groundwater samples have come from. If we go deeper down into the Upper Cretaceous, there's the Horseshoe Canyon Formation, which is a major CBM play, which was drilled in between 2006 and 2011 mainly. Further down, we have a Manville Formation in the Lower Cretaceous, which was also explored for CBM activity. And all the shale gas plays we have in northwestern Alberta and northeastern British Columbia are stratigraphically further down in the Triassic and the Devonian with the Montney, Horn River, and Duvernay Formation. So the Montney Formation here straddles the provinces of British Columbia and Alberta, and it's stratigraphically in the lower Triassic. The Horn River Basin, which is right up here, is a Devonian shale. So you see the location of the Horn River Basin, and that shale is of Devonian age. This diagram now uses a new parameter. We plot the dryness parameter on the y-axis. That's the concentration of methane divided by the concentrations of higher alkanes. In this case, it's ethane and propane. What we found is for shallow groundwater in Alberta, we typically get a dryness parameter which is higher than 500. So we sit here on top. And carbon isotope values, which are on the left-hand side, so all of these are shallow groundwater data, with delta 13C values of less than minus 58 per mil. If you go down deeper into the subsurface, into the CBM plays, we see dryness parameters of less than 500, and carbon isotope values start to increase to between minus 58 and minus 54 per mil for the Horseshoe Canyon Formation. And if you go deeper in the Manville Formation, we're even more thermogenic, with a lower wetness parameter and higher carbon isotope values approaching minus 44 per mil. The next diagram now adds the shale gas plays. So again, a diagram which now plots the gas wetness. That's the percent of all the higher ethane, propane, etc., divided by all the alkanes, methane to C5. We see very dry gases in groundwater with low carbon isotope values, less than minus 58 per mil. The CBM plays we just looked at have considerable wetness and higher carbon isotope values on average between minus 54 per mil for the Horseshoe Canyon and minus 49 per mil for the Manville. And if you then go down into the shale gas plays, so here you see data for the Doig Formation, for the Montney, and for the Horn River, we see variable wetness, significant variability in the wetness parameter, but carbon isotope values higher than anything else you have seen before, higher than minus 46 per mil, in some cases approaching minus 30 per mil. So if we then combine the gas wetness here on the left-hand side, use average values with the carbon isotope values, combining the wetness parameter and the carbon isotope values of methane, that yields distinct signatures for free gas from shallow groundwater and produced gases, both from the CBM plays, which are sitting up here, and for the various shale gas plays, which are sitting on the right-hand side. And because of that, we believe that combining both parameters is a very promising approach for monitoring for potential stray gas contamination of shallow aquifers. The last 3 minutes of my talk I want to spend on a different program. It's called the Baseline Well Water Testing Program, also conducted on Alberta since 2006, because the regulator required a baseline groundwater analysis for each groundwater well within 600 to 800 meters radius from a newly drilled coal bed methane well. Now, all of these are not monitoring wells. These are landowner wells. Various different consultants have gone out to these wells to take free gas samples, and the samples were submitted to various different companies or universities for chemical and isotopic analysis. So data quality control is a little bit more of an issue here, but the size of the data set is enormous. By now it's more than 12,000 samples, and the results are publicly available on this website. Now, out of all of these samples, about 1,200 yielded a free gas phase. We did a quality control screening on that and ended up with about 640 free gas samples for which we had believed good quality chemical and isotopic analysis. And I just want to show you a brief snapshot of the same parameters we looked at before. In this case, it's methane concentrations from 0 to 100% in the free gas samples. This is all the data together, and you see significant variability. The median value is 44% or so, but the Q3 is higher than 80%, and the Q1 is less than 2,000 ppm. So huge variability of methane concentrations. The 4 bars to the right-hand side subdivides the same data set into different groundwater wells. These are the shallowest, less than 30 meters. This is 30 to 60 meters, 60 to 100 meters, and these are the deepest groundwater wells. And it's not a big surprise that the deeper you go, the higher the median methane concentrations is. So again, despite that considerable variability of methane concentrations in this data set, once you look at the carbon isotope fingerprint of the methane for the entire data set, you see very consistent signature. The average value minus 67.2 per mil. Very little variability between the Q3 and the Q1 value in this box and Visca plot. And even if you resolve the data by depths, you see slightly more negative median carbon isotope values in the shallow wells, but in the deeper wells, the carbon isotope values are relatively consistent. In this landowner-driven sampling program, where various different companies and universities have contributed the data. Again, here we look at carbon isotope values of methane in free gas shallow groundwater. On the left-hand side, it's the data set you have just seen. On the right-hand side is a similar statistic for the GOWN data network, for which we have much fewer values. It's a much better constrained monitoring network, but essentially the outcome is the same. The median carbon isotope values of methane in shallow groundwater are only different by 2 per mil. And despite different monitoring approaches, we believe the obtained carbon isotope values are very comparable for baseline analysis and indicate that the majority of this gas is of biogenic origin with very few exceptions. So to conclude, methane concentrations in free gas of shallow baseline groundwater were found to be quite variable. And we think methane concentrations alone is not a reliable standalone monitoring parameter. Contrast carbon isotope values of methane in free gas from the same groundwater well were found to be constant, indicating that the methane comes from the same source in these particular cases. The combination of wetness parameters and carbon isotope values of methane and potentially higher alkanes such as ethane and propane, if they do occur, were found to be distinct between shallow groundwater and various conventional gas plays in Western Canada, and we think that's a very good trace approach once potential leakage occurs or is alleged. And finally, baseline data for free gas samples obtained from dedicated monitoring wells and from landowner wells were similar in the pre-drilling analysis. We don't say after a potential leakage has occurred that landowner wells might be the best monitoring tool. I think you're much better with using dedicated monitoring wells in this case, but for pre-drilling baseline analysis, the landowner wells gave us similar results to the dedicated monitoring wells. With that, I want to acknowledge financial and logistic support from Alberta Innovates, from Alberta Environment and Carbon Management Canada. Also want to acknowledge financial support from the University of Calgary and some of its programs. And I want to thank you for your attention. Thank you.
We have time for a couple of questions.
The similarity of the isotope values, is that common or unusual? Minus 67 and minus 69, what does that represent?
The question is whether
Being such a similar value, you can progress into other areas, and then what about mixing between, what would that, can you calculate the proportion of mixing between the things that
The question was whether the similarity of the carbon isotope values of the biogenic methane are normal for this area. Now, these are median values. There's a significant standard deviation around them. I've shown you individual values ranging from -58 to -94, depending on location where you are. So I think you have to do the fingerprinting for each given location to get a solid baseline analysis. On the monistic valve, where we had 15 analysis, the value was -78.5, so quite different from the average values I've shown. Once you fingerprinted your gases in the intermediate zone and in the production zone, and you have gas concentrations, isotopic fingerprints, you can calculate theoretical mixing curves and then assign to with which accuracy you might be able to distinguish stray gas contamination if it were to occur.